Hello geometry students, my name is Emigh, and this video is our discussion on section 5.3 and section 5.4, medians and altitudes of a triangle, title of section 5.3, which we will do first. A median of a triangle is a segment whose endpoints are a vertex and the midpoint of the opposite side. So you can see the median here. Its endpoints are the vertex of the triangle and the midpoint of the opposite side. A triangle has 3 medians, and all of those lines are concurrent. That means they meet at one point, called a point of concurrency. That point of concurrency, it turns out, is 2/3 the distance from each vertex to the midpoint of the opposite side. So to find parts or lengths of segments inside the triangle like this, we can use DC. Let's highlight that. That would be from here to here, and that's equal to 2/3 whatever the whole length is, DJ, like that. So something that might help. Okay, so let's take DJ, and we'll draw it like this instead. DJ. Okay, now we're talking thirds, so let's cut it into thirds. So let's put a point here and here. Okay, looks like we've got thirds there. Now let's give them some units, maybe 5, 5, and 5. Okay, so the whole thing. And let's put point C on there. C is right here. And okay, so the entire thing, D to C, is 15 linear units. Oh, hold on, not right. D to J, the whole thing, DJ, is 15 linear units. D, J, and C, 5, 5, 5. Okay, sorry about that. Okay, so DJ is 15 units. 2/3 of that is DC, so that gets 10 of our units. And 10 is equivalent to 2/3 of 15, so times 15 like that. So hopefully that'll help you get through these 2/3. Just think of everything in thirds. Take the total distance, divide it by 3. 2 of the thirds go here, and 1 of the thirds goes there. So let's highlight a different one. Let's change to a different color. Let's try to explain this again with purple. Okay, so let's go with this segment right here. Okay, so whatever that length is, you can divide it by 3. 1 of the thirds will go right here, and 2 of the thirds will be here. It's always going to be twice as long, okay? That's from that point there. So last one, this would be 2/3 of the distance, and this would be 1/3. All right, let's try to work with that. The point of concurrency of the medians of a triangle is called the centroid, and it is always inside of the triangle. Okay, using the medians of a triangle. So we are told that AC equals 10 units. And I always suggest you put given measurements like that on the figure. And we're being asked to find AE. So we want to know this whole thing here. Okay. I already know it. Without even doing the fraction work, what do you think it might be? Well, let's see if you got it right. Okay, so point C is in fact the centroid because it is the point of concurrency of the medians. And if we do our fraction work, then A to C is 10. 2/3 of that times AE. We would multiply both sides of the equation by 3/2. And we would get that the whole thing is 15 units. Oh, this just happens to be the numbers that we used in that little example that I sketched. So this is 5 units here, and then the whole thing would be 15. So this fraction work, it's good if your numbers don't work, aren't too easy to just see like this, but I'm hoping you just saw it. I'm hoping you just went, okay, that's 10, so this is half of that, which is 5, making the whole thing 15. The altitude of a triangle is the perpendicular segment from a vertex of the triangle to the line containing the opposite side. An altitude of a triangle can be inside or on the outside of a triangle, or it could be an actual side of the triangle. Let's take a look. So here we have an acute triangle, and you can see that if this is our base, okay, if this right here is our base, then that is our altitude. It's the height of it. It's like if you took a tape measure and you walked up to that triangle and you measured it, you would measure to the top point and straight down. If this was your triangle, an obtuse triangle, and here's the base of it, so let's say this is like a structure in your house, and you walked up to it with a tape measure and someone said, well, how tall is it? You would measure from this point right here straight down to the ground. That is the altitude. It's the red line. It is on the outside of the obtuse triangle. And if you have a right triangle, so pretend this is a structure in your house and that's the base. Someone said, well, how tall is it? You'd put the tape measure here, straight down, and that is the altitude. So in a right triangle, it's actually one of the sides. Now do remember that every triangle has 3 altitudes, because if you took this, let's say the middle one, and you rotated it, let's say it was like something in your house that you could actually move, and you rotated it so it was standing on this side. So you got to pretend this is the ground right now, okay? This is your carpet or something. And the altitude at that point would be, this is the tallest point to there, okay? The point of concurrency of the altitudes is called the orthocenter. The orthocenter will be inside of an acute triangle, outside of an obtuse triangle, and on the vertex of the right angle in a right triangle. Okay, let's work with the middle one. We've already got two going, so might as well see where they, so that's our altitude. And then I'll do, okay, if this one was the base, the height of it would be, this is the hardest one to see. It'd be that tall. Okay, so there are 3 altitudes. So let's extend them now to make them longer, just to see where they meet. Oh, this is a terrible job, sorry. But you can see there that they would meet on the outside. This figure is much nicer than mine. Using the altitudes of a triangle. So let's say we have triangle ABC. Vertices are at 1, 3, 2, 7, and 6, 3. What are the coordinates of the orthocenter of the triangle? Okay, so practice your graphing skills. If you haven't graphed in a while, pause this video and set up your rectangular coordinate system. Plot those 3 points, connect the dots so you can see triangle ABC. Welcome back. If you got something like this here, nice job. If you have a point that's off, make sure you make your adjustments. Okay, now we need to sketch the altitudes. The easiest one I can see would be, this is already on the ground, so the height would be B, so that's 1 altitude, okay? The other 2 aren't quite as easy. Let's pretend this was the ground next. If that were the ground, this would be the tallest point, so it's going to be straight to the, straight to the ground like that. Oh, made it dashed. That's cool. And then the last one, well, remember, you don't really need the third one because we already know the point of concurrency. It's right there where those 2 cross. If we were to do the third one, though, this would be the tallest point. So it'd be straight down like that. 90 degrees, 90 degrees, 90 degrees. And that right there is the point of the orthocenter. Ooh, but what is that? What are those coordinates? Maybe 2, 4? Using a ruler, it looks more accurately at 2, 4. But what if we're not completely sure if that is at the whole numbers 2, 4? What if it's like a little past 2? Well, we can write the equation of the red line and the blue line, and then we'll use our algebra skills to see where those two lines intersect. Okay, so the equation of the red line is the easy one. Any vertical line has an equation that starts out x equals, and then it's whatever number it passes through, so x equals 2. This one here, you can find the equation of the line. We have a y-intercept of 2, and we have a slope of rise 1, run 1, rise, run, rise, run, rise, run, rise, 1. So you could go with y equals mx plus b. Y equals a slope of 1x plus its y-intercept is at 2. And that's where the y equals x plus 2 comes from. Right, so now we've written what's called a system of equations, if you recall from algebra. And now we can use our algebra skills to solve this system. Looks like we're just going to start by substituting the 2 in for that x right there. If we substitute the 2 for the x, we get y is at 2 plus 2, which means y is at 4. So it actually is on that, at the whole numbers, located at 2, 4. Make sure you put it in parentheses, okay? For it to be a location, a point like that, it has to be in parentheses. I know a lot of times, not a lot, you may forget the parentheses and just write the 2, 4 like this, and it'll mark it wrong because this right here, this is a list of numbers. That's saying the numbers 2 and the numbers 4. This right here is totally different. That's a location of over 2, up 4. It's 1 point. List of 2 numbers, 1 location. Okay, so careful of that. Okay, section 5.4 is on midsegments of a triangle. A midsegment of a triangle is a segment connecting the midpoints of 2 sides of the triangle. Triangle midsegment theorem says that if a segment joins the midpoints of 2 sides of a triangle, then the segment is parallel to the third side and it's half as long. Okay, so 2 things: parallel to the third side and half as long. So what that means is that the red and blue lines here are parallel to each other, and the length of the red one is half the length of the blue one. Or you can think of it as the length of the blue one is twice as long as the red one. Whichever way, they're the same thing. We do want to make sure we have a mid-segment here. Mid-segment, D is the middle of this side. We know that because of the single congruent tick marks. E is the middle of this side. We know that because of the congruent tick marks. So this segment, this red one, it's connecting 2 middles, 2 midpoints. And that is what qualifies it as the mid-segment. Okay, so let's look at this triangle here. All 3 mid-segments are constructed. So here's one mid-segment. So it's going to be parallel to this side and half of its length. Let's do another one. Here's a mid-segment, which means it's going to be parallel to this side and half of its length. And the last one, this is a mid-segment, which means it's parallel to this side and half of its length. Okay, so we've listed the parallel sides part. And over here, we have that TR, so this distance is half of FE. All right, let's do the other 2. TS is half of DE. And finally, RS is half of DF. Okay, so a lot of things come about from the mid-segment theorem. 3 parallel statements and 3 equations using half or double. Okay, so using the mid-segment theorem to find segment lengths. Here we have triangle QRS, and we have T, U, and B as midpoints. So T, U, and B. So they told us that T is the middle of this side, U is the middle of this side, and B is the middle of this side. Okay, so we definitely have our midsegments, and we can use the knowledge that midsegments are half the length of the side they're parallel to find the lengths of TU, UB, and QR. Okay, so let's start with TU. So this one right here, it is parallel to this one, so it's half of its length. And this one's 40, so this one would have to be 20. Pause this video, try UB and QR. Welcome back. If you put, there's our 20. If you put 25 for UB, nice job. So we've got 20 here, 25 here, and if you put 60 for QR, you got that right as well. 60, because that's double the 30. Okay. All right, go ahead and put arrows on the pairs of parallel sides and midsegments, and then we're going to find angle EFD and FDE. Okay, so let's start with this first one. EFD. EFD. So we're being asked to find this right here. So I know, or we know, sorry, that this midsegment is parallel to this line here. Okay, that being so, we want to focus on the two parallel lines cut by the transversal that creates this angle here for us. Those two parallel lines aren't going to do it. Let's pick another pair. Okay, so we're trying to find these right here, this angle right here. So let's use these two parallel lines, 1 and 2, cut by this transversal. There we go. So we're going to use this line and this line, cut by this transversal, and that's going to help us to find that angle measure. Okay, so I'm going to go off to the side and redraw that because there's way too much going on in that figure for me to follow. So I'm just redrawing it like this. Okay, just the 3 lines that I need. Here is that the angle in question. Okay, these two are parallel to each other, and this one is the transversal. So I'm going to do one more thing. I'm going to extend my parallel lines, cut by a transversal. Just makes it easier for me to see what's going on. Okay. So hopefully you can see that we have redrawn this one, and this one. Okay. And now we can also put our known angle measure of, what known angle measure do we have? We have, oh, here we go. We've got the 73 and the 36. Oh man, we're actually going to have to use 2 different parallel lines cut by a transversal. Wow, because the 36 and the 73 don't go on this figure. Okay, well, no problem. Trial and error. Here we go. This is our angle of interest. And the problem with those ones, the 3 lines that I chose, is we didn't bring along the 73 or the 36 with those 3 lines. But we need one of those. We need the 73 or the 36. So I know I have to use this one and this one. No other options. Those 2 have to be selected. But the third one selected needs to be this one because that one brings along the 73. Ooh, it's a tough one. Okay, but we got this now. So hopefully, even though I screwed up, hopefully that can show you the thought process behind what it takes to determine your 3 lines that you need. Okay, so I'm taking this line, and this line. Okay, so they're drawn over here separate. And what I'm going to do now is carry the 73 and the question mark. All right, now we're talking. And then I'm going to extend the parallel lines and extend the transversal. That's just my preference. I like to see the 2 parallel lines cut by a transversal. So this is like, we learned it as L, M, and T most often. And now the 73-degree angle and the question mark angle are corresponding angles. It's because they're in the same location, this intersection and this intersection. The 73 and the question mark are in the same spot. And we know that if 2 lines are parallel, then corresponding angles are congruent. So this angle in question is also 73 degrees. Whew. A lot of work to get that. Okay. Let me erase that work there. So we have RS is parallel to DF, single. And we have our angle measured there, 73 degrees. Okay, now we got to do B. All right, this one's going to go a lot smoother. I know it. Okay, FDE, measure of angle FDE, FDE, F to D to E. Okay, so we know 2 of our lines. We have to use this one and this one because those are the 2 that create the angle in question. So we'll put a question mark there. Now we need to select our 3rd line. It needs to be parallel to one of those 2 we've already selected, and it needs to give us some measurement. Okay, well, this is an option because it's parallel to DF, but if we choose those 3 purple lines, we don't bring along the 73 or the 36, so that's not going to work. So we have this one and this one. All right, let's try this one here. Those 3 lines capture the angle in question and the 36, and they're parallel. All right, so those are going to be the 3 lines we need. You might even be able to see it right here that those 2 angles, the question mark and the 36, they're in corresponding positions, which means our angle in question is 36 degrees. But if you don't see it, no problem. I'm going to draw it over here separate from all of that going on in the figure. So it looks like that. That gives us the 36 degrees and the angle in question. And now what I'm going to do is extend those lines so it looks more like the way we learned it. 2 parallel lines, let's say L and M, cut by transversal T, let's say. And now maybe it's more obvious to you that these 2 intersections, the question mark and the 36, are in corresponding locations. And we know that if two lines are parallel, cut by a transversal, then corresponding angles are congruent, which means they have the same measure. And after all that, we can state that ST is parallel with ED, the transversal was DF, and our measure in question, our angle in question, FDE, has a measure of 36 degrees. All right, let's use the midsegment of a triangle to find a distance that we otherwise wouldn't have been able to find. So check out this figure. We have a sinkhole, and we want to know the distance across it. Okay, well, maybe you don't have the right tools to measure from point A to point B. So how are you going to find out the distance from point A to point B? Well, it's over the water, so you may not have the right tools, like I said, but you may have the tools to make measurements on the ground, on the grass part where you can walk. So imagine yourself start here at point A, and you'll just walk out here. And when you walk, you'll want to measure what that distance is, and you'll want to mark off what half of it, where the middle of it is. Okay, now you got to do a little more walking, okay? Now you walk over here to point B. And when you measure that distance, make sure you mark off where half of it is. Okay, that's something we can do on the ground. Walk here, walk there. Note the two measurements. Draw your figure. You got half and half. Now what that means is the connection of those two dots, the connection of the middles, see how it's on the grass? So you can measure that, and it's 46 feet, which means you can multiply that by 2, and you will have the distance across the sinkhole. 92 feet. So next time you find yourself wanting to know the distance across a sinkhole, you can use your geometry skills and impress your friends. All right, that will conclude our discussion on section 5.3 and 5.4. My name is Emigh. Thank you for joining me, and I will see you next time for our discussion on section 5.5.